In this video, we are going to discuss about single electron transfer mechanism. Simply, we say as set mechanism. Already, we have discussed the reaction mechanism that involves electrophile and nucleophile. If you recall, the nucleophile, say carbanion or negatively charged species, adds to electrophile to give the product. These two electrons are used to make bond between carbon and electrophile. Basically, two electrons are added to electrophile. Similarly, if you go for nucleophile which has lone pair of electron, in that case also the lone pair of electron is used to make bond. Two electrons are given to electrophile. After that we get plus charge here. Next one, let us go for alkene. In that case also this pi bond attacks the electrophile to give this one. Here also this pi bond is equal to 2 electrons. So in all these cases 2 electrons are added to electrophile. Is there any possibility to add 1 electron? Yes, it is possible. We can add 1 electron to the electrophiles. At this point, I would like to discuss about the oxidation potential of metals. You might have come across the oxidation potential in electrochemical series. Generally, metals as such, they are not stable. If you go for metal in zero oxidation state, they are highly unstable. It tries to lose its electron and it tries to achieve the more stable oxidation state. Only a few metals exist as such in the nature. They are known as native metals like gold and silver. They exist as such. Now if you go for alkali metals like lithium, sodium, potassium, they will not exist as such even for a few minutes. If you keep that open, immediately they will get converted into lithium hydroxide or sodium hydroxide, potassium hydroxide, like that. That means they lose 1 electron. So I use this term to be easy. So it is 1 electron, not 1 negatively charged species. It is not lone pair. It is 1 electron. The reason, when it loses 1 electron, it gets more stable electronic configuration. In the outermost shell of lithium, there will be 1 electron, 1s2, 2s1. By losing the 1 electron, it becomes more stable. That is the driving force behind this. Similarly, if you go for magnesium, this can lose 2 electron and it can become Mg2+. Again, the electrons are not given as negative charge. They are 2 electrons. You should not consider this electron as the minus charge, whatever we use in carbanion or alkoxide. So it is 1 electron, like that 2 electrons are given. Now I go for few more metals like zinc. This also can give 2 electrons and it can become zinc 2+. The electronic configuration of this 3d10 4s2. So it can lose these 2 electrons to become zinc 2 plus. Another one, titanium 3 plus. As such, you go for titanium metal, it will have 4 electrons in the outermost shell. But if you go for titanium 3 plus, it will have only 1 electron in the outermost shell. By losing that, it will become titanium 4 plus. So these are some of the most common metals which readily gives single electron. Now let us see the reactions of these metals and its application. Before going to that, I would like you to recall the electrophiles. I categorize the electrophiles as carbene, nitrene and benzene. This is the first category. The second category, carbocation and H plus. So basically positively charged species. Third one, atom attached with more electronegative atom via single bond, double bond or triple bond. For example, I go for halide, even I go for alcohol, acid, aldehyde, ketone, ester, goes like this. In this case, this is more electronegative, so we get del plus on this. This is more electronegative, so we get del plus. Similarly, del plus here, del plus. This is the second category. Third one, alpha beta unsaturated system. In this particular carbon is del plus. Similarly, when you go for electron withdrawing group, this and this, they are electrophilic. So this is how I categorize. So I categorize into 4 different types. Now, is it possible to add single electron to these electrophiles? These two are generally known as intermediates. We cannot generate intermediates in the presence of the metals whatever I have mentioned earlier. So because of that, we can skip these two categories. So the metals and the intermediates and the condition whatever we use to make them, they are not compatible. What about the remaining two categories? Yes, it is possible. We can add single electron to all this electrophile. Not only that, even we can add single electron to the last category of nucleophile. If it is strong nucleophile, we cannot add. This alkyne and aromatic ring, they are weak. So we can add single electron to them because the nucleophilicity of them is very less. And you cannot add to carbanion or alkoxide. But you can add electron to alkyne and aromatic ring. Now let us discuss one by one. First, I go for acid. In carboxylic acid, we have del plus on this carbonate carbon. Also, we have del plus on this because oxygen is more electronegative. Now what happens when I add lithium to this or sodium to this? Lithium gives one electron here. Remember, this minus you should not consider as carbanion. It is only one electron. One electron is donated to hydrogen. Then this goes over oxygen. What we get is, and this minus combines with lithium. What about this hydrogen? This hydrogen will get one electron. This will combine with one more H. They will combine to liberate hydrogen. When you add alkali metal to acid, this is the reaction. Basically, one electron is transferred to more electropositive hydrogen atom. We get carboxylate. Not only this, even if you go for alcohol and if you add lithium, the same reaction will take place. Lithium or sodium. What you get is liberation of hydrogen. Suppose if you add this to phenol, you will get phenoxide. The mechanism is same. What about other metals? Can I go for zinc or magnesium? No. They are somewhat less reactive towards this hydrogen. Alkali metals which are highly reactive, they will undergo such liberation of hydrogen from the compound which has acidic proton. The next functional group, it is Alkyl Halide. Okay, general, you can say it is X. Since halogen, it is more electronegative, we have del plus on this. When I add sodium, sodium gives one electron. That one electron will be on this. This minus charge falls over iodine. So this bond I have placed on iodine. It has given one electron. So now I have got CH2. It is not radical, it is one electron. Further, one more electron, I write like this, will be given by another equivalent of lithium. We get minus charge. Now 2 electrons has been donated, so that is equal to minus charge. This, as soon as this minus charge is formed, it is nucleophile. In the reaction mixture, we have unreacted alkyl halide also. Immediately this will attack, and what you get is the coupled product. So alkyl iodide, in the presence of sodium, we get the coupled product, that is called Woods coupling. So basically it involves transfer of single electron to electropositive atom. I go for ester. When I go for alkali metal, say sodium, the electrophilic position in this is this carbonyl carbon. So the electron, single electron, will be delivered on this carbon. When it is delivered, this bond migrates over oxygen. Further, one more electron can be delivered. Because of that, we may get this one. Now this minus charge, carbanion, it is nucleophile. It can take proton and we get hydrogen here. The next step, two oxygen atoms are on the same carbon. So it eliminates ethanol or sodium methoxide, we get aldehyde. If you repeat the same steps, whatever you have done here, the product, whatever you get, will be like this. One more hydrogen will be added. Another electron will be delivered here. This bond will go over oxygen. One more electron will be delivered. We will get minus charge. That will take proton. We will get alcohol. So basically, I have reduced ester to alcohol. This cannot be achieved by sodium borohydride. We have to go for LAH. LAH is somewhat expensive. Sodium is cheap, but it is dangerous to use. In industry, they go for this particular method to reduce ester because it is cheap compared to LAH. So this particular method is known as Bowelt blank reduction. It involves single electron transfer. Here itself it is very clear, aldehyde can be reduced via single electron transfer mechanism. What about ketone? Can we reduce ketone with sodium? Yes, we can reduce. It can be converted to the corresponding alcohol. The mechanism is same. But this can be easily reduced by sodium borohydride. So the condition with sodium borohydride is somewhat easy. But this particular method is generally used for the preparation of pinnacle. Generally, instead of sodium, we use magnesium. It will not give electron that much readily. The reactivity is somewhat less. When you add this, magnesium will donate electron, and what we get is this one. Similarly, imagine one more molecule like this. I have not donated one more electron on this. If I donate, it will become minus. Then that will be reduction of ketone. Instead of that, I have donated one electron. Then I have made a bond between these two. This bond is made up of two electrons now. What I get is pinnacle. So the pinnacle, whatever we use in pinnacle rearrangement is prepared by this method. Take the ketone, treat with magnesium. It will undergo single electron transfer reaction. You will get pinnacle. If you add magnesium, what will happen? You may know we get Grignard reagent. What is the mechanism? It is nothing but single electron transfer mechanism, or you can say insertion. I can explain this based on single electron transfer. Initially, one electron is donated. So what we get is basically electron. Now, to this I add one more electron. It becomes RCH2 minus, and we have Mg2 plus as well as Br minus. So the Br minus, whatever has been formed, the minus, whatever I got after transferring two electrons sequentially, I have got this. Now this, everything together give this. Similarly, you can propose mechanism for Riefer-Matsky reaction. If you add zinc to ethyl bromoacetate, then the reaction will take place. Not for simple alkyl halide. When there is electron withdrawing group and the halogen is alpha 2 electron withdrawing group, then the reaction is more facile because the reactivity of zinc is somewhat less. So this particular reaction is known as Riefer-Matsky reaction. The earlier one, it is nothing but Grignard reaction. A similar mechanism you can propose for palladium 0 also, that is basically palladium catalyzed reaction. But generally we don't refer this as set mechanism. We say as insertion, oxidative insertion. In this case also there is oxidation and it has got inserted. In this case also there is oxidation of metal and it has got inserted. So we use the term insertion, not single electron transfer mechanism, but it can be explained based on this mechanism. What about alpha beta unsaturated system? In this case, the beta carbon has del plus. If I add lithium, electron will be delivered here. We will get this intermediate. Further, one more electron will be delivered and we get minus charge that will take proton. We will get hydrogen there. So finally the product, whatever you get, will be like this. If you compare, I have reduced the double bond. So to reduce the double bond selectively in alpha beta unsaturated system, we use lithium liquid ammonia. The reaction involves transfer of single electron to electrophilic position of alpha beta unsaturated system, that is beta carbon. Now let us go for nucleophilic carbons. Alkyne, basically it is nucleophile, it is not electrophile. To this also electron can be added. When I add single electron to this, the minus charge, this bond goes over one carbon and the electron is delivered on the other one. So you can imagine this electron is delivered here and the minus charge goes over the other carbon. It prefers to exist trans. So this and this, they are trans now. Now the product, whatever you get after abstraction of hydrogen, will like this. Further, one more electron will be delivered and we get trans product. To reduce alkyne selectively into trans alkene, we use lithium and liquid ammonia. The next method is very well known, Birch reduction. You can reduce this with lithium and liquid ammonia. Metal gives one electron. It can be delivered anywhere. When it is delivered, we get intermediate like this. You can consider like this. This electron is delivered here. This bond goes like this to give this intermediate. The minus charge can be placed on this carbon also. Since it can be in resonance, you can place on this as well as here. But when you place the minus charge on fourth carbon, the minus charge and the electron, they are kept at the maximum distance. That's why it goes to that carbon. Now it can take H plus, we get hydrogen. Once again one more electron will be delivered, that also will take hydrogen to give this. Suppose if I go for this compound, now the question is where the single electron will be delivered. We have 4 different positions where the electron will be delivered. Because of electron withdrawing group, we have del plus on this as well as on this. So electron should be delivered either here or here. Ortho and para position are electrophilic. So the electron can be delivered either here or here. Based on that, I go for the intermediate. This is one intermediate. The electron has been delivered to the para position. The another one will be like this. The electron has been delivered to the ortho carbon. I have placed the minus charge here because it will be resonance with electron withdrawing group. I can further go for resonance and I can bring this minus on this carbon also. When it is here, it is not resonance stabilized. When the minus charge is on this carbon, it is resonance stabilized. That's why I have placed here also on this carbon. Now in this, the minus charge and the electron, they are very close. So this one will not be preferred. This one is more preferred. So further, the product, whatever you get, will be like this. A similar reason can be given for electron donating group also. In electron donating group, ortho and para are electron rich. These 3 positions are nucleophilic. They have rich electron density. But this particular position, electron density is same as benzene. The electron donating group cannot increase the electron density on metacarbon. It remains same as benzene or almost same as benzene. So the electron can be delivered here. I go for that. When it is delivered, we get this intermediate. They have been separated by maximum distance and the electron has been delivered to the metacarbon. Further, the product, whatever you get, will be like this. What about pyridine? The lone pair or nitrogen is not involving in resonance. Because of that, the electron density on these carbons cannot be increased. Since nitrogen is more electronegative compared to carbon, it will try to pull the electron. Because of that, we get del plus on this, goes like that. The maximum electropositive character is on this carbon because it is very close to electronegative atom. But when we go for reaction, we are not getting this one. Instead of that, we get this intermediate. The reason the minus charge should be placed on nitrogen, since it is more electronegative, it can pull the electron density, electron cloud. So the nitrogen prefers to take the minus charge. After that, if I place the electron here, the minus and the electron, they are very close. So this is not preferred. On the other hand, in this, the minus charge and the electron, they have been separated by maximum distance. So this is more preferred. Because of that, the product whatever we get will be like this. So overall, we have seen several name reactions and very important reactions. The first one, Woods, Grignard, Reformatsky, Bowolt, blank reduction, Birch reduction, reduction of alkyne, reduction of alpha beta unsaturated system, separation of acidic hydrogen. This is observed from acid, alcohol and phenol. It is very easy to identify single electron transfer mechanism. Generally, there will be metal. If you find metal not in the oxide state as such, if you find metal, then you can go for single electron transfer mechanism. There is only one reaction in which we don't use metal. Instead of metal, we go for salt, but it is not more stable oxidation state. That is titanium trichloride. Titanium prefers to exist as titanium tetrachloride or titanium 4+. The electronic configuration, it will be 3d2 4s2. If I remove 3 electrons, then the electronic configuration will be 3d1. That is not stable. By losing this, it will become more stable. So for titanium 3, it is 3d1, but for titanium 4, it is 3d0. It tries to lose the electron, so it can act as source of single electron. In this, the ketone is treated with titanium trichloride. Sometimes they go for titanium tetrachloride with reducing agent like zinc. When you go for this, the product whatever we get will be alkene. So they undergo coupling to give this product. It will eliminate titanium dioxide and we get alkene. So ketones are converted into coupled alkene by treating with titanium trichloride. In this particular case, we are not using metal. We go for less stable salt.